Very good morning, students. So yesterday only we had a class, and we had seen that how pumping lemma works, and we had seen a few examples of how can we use pumping lemma to prove that a language is not regular. And we had also seen that it's not possible to use pumping lemma to prove the reverse, that is to prove that a language is regular, right? So, more or less a portion of pumping lemma is done. You can always explore more examples, as I had already told you yesterday. So today what I am going to do is some of the miscellaneous parts of your regular language is left, or I should say DFA is left. So I am going to cover them today, and in the next week I will start with regular expressions, which is a separate broad topic. So I am not going to start it in this week. So I have planned to cover some miscellaneous portions which are left in today's class, right? So let me just share my screen. Is my screen visible?
Yes, ma'am.
Okay. So the first topic that I am going to cover in today's class is how can you eliminate epsilon moves in a epsilon NFA. So we have already seen that we are well acquainted with two flavors of NFA. One is a normal NFA and one is the NFA with epsilon moves. Now you might be asked at some point of time to remove the epsilon moves from a given NFA. Now there is some particular process to do the same. So we are going to see how to remove the epsilon moves from a given NFA, right? So these are the steps which are being depicted here. So if it's an epsilon NFA, we are assuming that we have two states, S1 and S2, and there is an epsilon move in between S1 and S2. Okay. Now we have to find all the edges starting from S2, that is this state from where the epsilon move is going. So we have to find all the edges starting from S2 and then duplicate all the edges to S1 without changing the edge labels, right? So whatever edges are starting from S2, we are going to duplicate the same from S1 without changing the edge labels. Now again, what else we need to do? If S1 is the initial state, we need to make S2 the initial state, and if S2 is the final state, we need to make S1 the final state. These are the set of steps that we have to perform for removing epsilon move. So let's see an example. Let's look into an example. This is a epsilon NFA. As you can see, there are two epsilon moves over here, and we have total 1, 2, 3, 4, 5, 6, 7 states, wherein Q0 is the initial state and Q6 is the final state. Now whenever you have two such epsilon moves in a particular NFA, or maybe more than one epsilon moves in a particular NFA, now how to decide that which epsilon move to remove at first, because that sequence basically matters. So what we are going to do is we are going to start off with this epsilon move. Why? Because if you see, after this Q4, we do not have any further epsilon moves. That is why it's safer, or it's the correct way to remove this epsilon move at first rather than removing this, because even after this we have another epsilon move. Suppose you had another epsilon move over here, then you would have removed this one at first, and then this one, and then this one. Okay. So in our case, we have an epsilon move over here which we are going to remove at first, and then we will go for this one. So just assume this one is S1, that is Q1 is equivalent to S1 and Q4 is equivalent to S2. Just to maintain the symmetry of this process, this is S1 and this is S2. Now what was the first step? Find all the edges starting from S2. This is S2. What are the edges starting from S2? You have one edge towards Q5 with a label 0. Then we need to duplicate all edges to S1 without changing edge label. So we need to duplicate the same edge from Q1, right? From S1, so here S1 is Q1. So you look at this. I have drawn an edge from Q1 to Q5 with an edge level 0. This one remains intact. You need not remove this. You just remove this epsilon move and you add this extra transition from Q1 to Q5 with edge level 0. That is, you are replicating this edge. Okay, done. Now what was the third and fourth step? If S1 is initial, make S2 initial. Now see, out of Q1 and Q4, none of them are initial states, none of them are final states. So step number 3 and 4 are irrelevant for this portion. You are done removing this particular epsilon move. Now we are not yet finished. We have to remove this epsilon move as well, right? Because we had two epsilon moves. Same process, just check all the edges starting from S2 over here. Which is S2? This one is S2. Obviously this one is S1 and this one is S2. So what are the edges going out of S2? This is the edge going out of S2. If you see, this is the edge going going out of S2, right? So not only this one and this one, you have two edges going out of S2. So you need to replicate the same from S1. So if you see, I have added an edge from Q0 to Q3 with level 0, that is, I have replicated this one, and I have also marked an edge from S1 Q0 to Q5, that is, I am replicating this edge Q1 to Q5. So I will add the same Q0 to Q5 with the edge level 0. Okay. Now after doing this, let's look at the step number 3 and 4. If S1 is initial state, make S2 initial. So obviously again we will remove this edge, this epsilon move, epsilon transition. Now if S1 is initial, make S2 initial. So S1 was initial here, so we need to make S2 initial as well. Okay. Achha. Now someone might ask that, ma'am, till now we have seen that like all the examples that we have seen, in those examples we had encountered only a single initial state, right? Multiple initial state was not encountered in any of the questions. So I had checked some books and resources, and it's a bit controversial. In some of the books, resources, they are saying that in an NFA, multiple initial states are possible. And regarding this particular process where we are converting up epsilon NFA to a normal NFA, also I have checked that yeah, in some cases they are following a process which ends up in two initial states. So I guess it is allowed for NFA. It is allowed in some cases, though it's I will still say it's a bit controversial, but as I have seen in some resources, it is possible. So here in the same way we have two initial states. Q0 was already the initial state. Now again we are also making Q1 the initial state according to our step number 3. Okay. Now one more thing which was not given in this series of steps, we have to check after getting this final NFA where no epsilon moves are present. We have to check one thing, that do we have an unreachable state? That starting from the, what is an unreachable state? Unreachable state is something which is a state where you cannot reach starting from the initial state. That is, you start from Q0 but you cannot reach that state by any way. So over here in this particular NFA, if you see,
Q4 is the unreachable state, I think,
yeah,
because we cannot reach to Q4.
exactly, Q4 is the unreachable state because you can not reach Q4 by any means if you start from Q0. So what I'll do is I'll just remove, I have not drawn the diagram again over here. We are going to remove Q4. Simply remove Q4 and the edge going out of Q4. Rest the diagram will be same. We will just remove Q4 and the edge going out of Q4, and that would give us the final NFA without any epsilon move. Okay. So is there any doubt or any confusion regarding this procedure of converting an epsilon NFA?
Yeah, there was one doubt that why an extra edge is coming between Q0 and Q3.
Wait. So see, q0 and q3, right? So here we had an edge from q1 to q3 and we had an edge from q1 to q5. We have two outgoing edges from q1, and according to our algorithm or whatever you say it is, we need to replicate all the outgoing edges of S2 to S1. So this is one outgoing edge, this is another outgoing edge. So to replicate this one, I have added Q0 to Q3 with edge level 0, and again Q0 to Q5 with edge level 0. I have just replicated these edges according to our algorithm. Okay.
Ma'am, I have one another doubt that you said that this rule is applicable for each and every edge which is coming from S2, and we are, I mean, connecting the edge from the previous node to the real destination. So, is it applicable for loops as well? Suppose S2 is one kind of loop, so loop means it's also an edge coming from S2, and it is also have the destination S2. So then S2 will be connected with
Yes,
S1.
yes,
In that,
yes,
it will be
yes,
applicable for loop as well.
yes, 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 yes.
Okay.
Someone had written something in the chat box. Yes. Ma'am, according to this language, what should happen when Q0 or Q1 gets input 0? Q0 or Q1 gets input 0. Okay. So Q0. So Q0 on getting input 0 would go to Q5, and what else was written? Q1. Q1 gets 0, right? So Q1 also, when it gets 0, both Q0 and Q1, when they'll encounter a 0 transition, they'll move to state Q5. Like I
But ma'am,
Actually, there are two paths from Q0 and Q1 and 0. They can reach Q3 as well.
Yeah, this is a NFA. It's possible, na? You can either go to Q3 or go to Q5. Both are possible. It's yeah. We are not making it a DFA. It's a NFA. It's still a NFA. We are just removing the epsilon moves. So we can either go to Q3 or go to Q5. And according,
but ma'am, can we consider this process as a conversion process of NFA to DFA? Because in some books I watch this process they are doing for converting from NFA to
from
DFA.
NFA
Or
from NFA to DFA. See, from NFA to DFA, we basically, if you do not have a epsilon move, then it's quite easy and straightforward. We are like making like sets and doing it. Now, if we have a epsilon move, I am not very sure this process is going to work. Like. It can work basically, but then you will have to break the process into two steps. First you will convert the epsilon NFA to a normal NFA, and then again you have to convert the like normal NFA to DFA, whereas we have got a concrete process for doing it directly. Like I had shown you a process where we have an epsilon NFA and we can directly convert it to a DFA. We need not need to go through an intermediate stage actually. So and that is a well proven method actually, because what I was also seeing, that many websites and many resources are showing different methods, but all of them are not very what should I say, reliable, because sometimes what happens, they take an example, they show the process with that example, but when you try it on some other DFA maybe or some other NFA maybe, it fails to work. But the process I had shown you for converting an epsilon NFA to a DFA, it's a very conventional process. It's there in all the books of automata that we normally read, like your Mishra, Chandrasekhar, Peter Lyons, everything. So I think it's more, it's safer to follow that process for converting an epsilon NFA to a DFA rather than breaking it into two parts and first converting this to an NFA and then to DFA. And this process I had checked many books and many resources to find the conventional method for converting or removing epsilon moves. I got this one in many from many resources basically. So for this I can rely, like for this portion I can rely upon this process. But as you were saying, for the conversion of epsilon NFA to DFA, if you ask me personally, like I would say no. And if you still want to try it out, then I would suggest at least try it with 2 or 3 like processes, like 2 or 3 epsilon NFAs you have, and try to convert them to an equivalent DFA. And if you are getting the correct answer, if you like can check it out that yeah, I'm getting the correct answer, then maybe you can go for it. Because if the answer is correct, I don't think that there will be a problem. Okay.
Okay, I understand.
So yeah, this was one topic I wanted to discuss. Now I have another topic for today. Just a second. I had no time to prepare a PPT, so I'll just use a canvas. So see, you have seen DFA, and you have also seen grammars. That is regular grammar, not a context-free grammar or something like that. If you remember, when I was teaching you all grammar, I had told you about right linear and left linear grammars. So there is a process of converting a given DFA to a grammar. Again, a regular grammar, because DFA is for regular language, the corresponding grammar is a regular grammar. So we can have a process for converting a DFA to a regular grammar. Okay. Now I'll just draw a DFA and try to convert it into a grammar, right? So I'll just take a small example. So sorry for the overlapping. So A is the initial state, and then we have a transition with small a. Then we have the state B, which is the final state, and we have a transition for A comma B. So this is not a DFA, basically it's an NFA. So I'll just add a n over here. So a DFA or a NFA to a regular grammar. Okay. So the simplest process for converting this DFA or NDFA, not a DFA, NDFA, to a regular grammar is I can convert this directly to a right linear grammar. Now, do you remember what is a right linear grammar? Right linear grammar was any grammar of this form. You know, like this. What was the speciality? The non-terminal symbol was on the right hand side. This non-terminal symbol was on the right hand side of the terminal symbol. That is what we call a right linear grammar. So if you try to convert this particular NFA to a right linear grammar, starting from this like first initial state, you have the state A, which is equivalent to this like this non-terminal symbol A is equivalent to the state A. So from A, on getting a A, we go to state B. Simply you can convert this transition to this grammar. We are we are in this non-terminal symbol A, and then we can move to this another non-terminal symbol A with this terminal symbol A over here. So this part can be converted to this part. What about this part? Similarly, this part can be written as B, and then you have A. This you have a self loop, right? So you have a AB or a BB. And one more important thing, since this is a final state, for any and every final state you need to add a epsilon in the grammar. Any NFA or DFA where you have got a final state, for the grammar of the final state you need to add this production rule. For the production rule of that grammar you need to add an epsilon. Okay. So this is the straightforward right linear grammar for this NFF. As you can see, all the non-terminals are present on the right hand side. But if you are asked to convert this into a left linear grammar, on a contrary, if in the question it is specifically mentioned that you need to find the left linear grammar for this NFA. Now what is the process? Now someone might say that ma'am, what if I just reverse the grammar? Let's try reversing the grammar. So reversing the grammar would give you, and over here it would give you now. Can someone tell me, is this a correct grammar? Like using this grammar, can you get this DFA, or is this the equivalent grammar for this DFA? Is it correct? This one and this DFA?
No, ma'am.
No,
It
ma'am.
is not correct, because it's becoming the reverse thing. It's not giving the same strings as that this DFA should give, right? So this is not the correct way of changing the DFA to a left linear grammar. So this is not the correct way. So what should we do? The steps for doing it is, we have got the DFA, right? Sorry, NFA over here. Reverse this finite automata. So we need not reverse the grammar. At first we need to reverse the finite automata. So let me rub this portion. So how to reverse this? Just you need to reverse the edges. So we had A and we had B. So just reverse it, will be A, and this will be A comma B. This will be the initial state, and this is going to be the final state. Okay, so look at this one. I have reversed the automata. Here you have reversed the edge, this edge of A, and here A was the initial and B was the final state. Since I have reversed the entire thing, now this one is going to be the final state, and this is going to be the initial state, and the self loop would remain same, because here the self loop was on the final state, here the self loop is on the initial state. So I have reversed the grammar, reverse the finite automata. Okay, now you have to find the right linear grammar for this reversed automata. So we already know how to find the right linear grammar. So
Ma'am, I have one question that in the given question, the languages are starting with the symbol A, but in the next when you reverse it, it may start with
yes,
B.
yes,
So I think
it
it's not.
can it can start with B. I have not completed the process. Once I complete the process, you will see that the grammar we get will be equivalent to this one. Okay.
Okay,
Yeah.
okay, ma'am.
So the right linear grammar for this particular reversed NFA is going to be basically it will start with B, right? So it will start with B. I can have AB. I can have BB, and I can have AA, right? And I'll have, since A is the final state, I'll have this one, right? Now once you are done with this, you have to reverse the grammar. You reverse this grammar. Okay, so how to reverse this grammar? B2, BA, BB, AA, A. Okay. So now if you check for this NFA and this grammar, I think you will understand that whatever language, whatever strings this DFA is giving, you can get similar kind of strings from this grammar as well. So we have successfully converted the given NFA to a left linear grammar. As you can see, the non-terminal symbols are on the left hand side. So this is basically a left linear grammar. If you try to derive a string, suppose something starting with A, like AB, right? So AB should be accepted by this, like generated by this grammar. Okay, how can we get AB, by the way? Just let me check. So we can have BA, then no, we can have BB, sorry, we can have BB, and then we can change, like remove this B with, or replace this B with A, this B remains same, and this A we can replace with epsilon. Okay, so we are getting AB. I guess it's correct, and it will work for any other string. So basically these are the steps for converting a NFA, or I should say a finite automata, maybe a DFA, maybe it is a NFA, whatever it is. You can convert it to a right linear grammar directly, and if you ask particularly to go for a left linear grammar, you will follow these steps. What are the steps? First, reverse the given finite automata, then find the right linear grammar for the reversed finite automata, and then you reverse the grammar itself. The grammar you get will be the left linear grammar for the initial finite automata that you had in the question. Okay, is it clear? Any doubt?
So in general, we are just first converting the, I mean, direction of all the edges, and then we are finding the grammar, and then at the final stage we are reversing it,
Yeah,
right?
yeah, exactly.
And so, ma'am, another question, that in the question there's only two nodes A and B, so that's why A is in the question, A is the initial state and B is the final state. So the next step, you are just reversing the direction. So B is the initial state or A is the final state. So because we have only two nodes, so one is initial and one will be final. So suppose if there are many numbers of five or six nodes are there, so suppose there's out of five, one is initial and all the others, I mean, suppose two are there who are final state. So which one to make initial state in that case?
Uh,
I mean, suppose there are two final
yeah,
states.
once more, tell me once more, if there are two final states.
Yes, if there are two finals and many more edges, suppose five or six, I mean,
No,
nodes are there, and out of the one
see,
is
making two or more, having two or more states won't be a problem. But if you have more than one final state, just let me think. You are reversing the edge. I think I'm not very sure. The initial state will only become the final state. Okay, because I am not finding the complement of the DFA, I am reversing the DFA. So basically I think the initial state will only become the final state, because the direction is getting reversed. Still I need to check this, okay, because I'm not very sure, and I don't want to give you a vague answer. I'll check this out and let you know. Okay, what is the proper way of reversing a finite automata, like any automata having more than two states, or maybe three or four states. I'll check it out and let you know. Okay.
okay, ma'am. Actually, there will be no problem with the final state because we have only one initial state, so we will initially the
Yeah,
final.
yeah.
So there's only one state, and multiple final states are
Yeah.
there. So which one will be
Yeah,
initial?
yeah,
That is
yeah.
the
That for that only I wanted to check the thing out. I'll check it once and let you know. Okay. Okay. So this was the process for converting a finite automata to a grammar. Next, one more thing. We, I'll just I want you all to know the reverse thing. That is given regular grammar to the finite automata. Now see, I am showing this for a right linear grammar. Again, there is a process for left linear grammar, but I am not going to that details. You can check it out yourself. I think you will get that from different books or websites. If you want, you can check. But again, I am not going into that details. I will just simply give you a right linear grammar and show you the process for converting it into a corresponding finite automata. Okay. So my grammar is something of this form. A is moving to AB, and then I have BA, and then I have B, and I have another non-terminal B which is going to AC, then I have B, and then again I have one non-terminal C which goes to AA and BC and A. Okay. So this is quite easy and straightforward. Just by looking at the grammar, you can easily change this into a finite automata. As you can see, there are three, symbols, non-terminal symbols. There will be three states, A, B, and C, right? So you can see that from A, we are moving to B with a terminal symbol A. So I'll just put the transition from A to B with a with the terminal symbol A. Then again we have A to A with the B symbol. So A to A with a B is initial state again. A. Next we have B. So B moves to C with A. B moves to C with a terminal symbol A, right? And then we have B to B with a transition of B. Then we have from C to A, from C to A with the transition of A, then C to C with the transition of with the transition of B. This is good, but you need to find out the final state. Okay. So for finding the final state, listen to this very carefully. You have to consider each production. This is one production, this is one production, this is one production. Now considering the first production, which is the only terminal symbol over here, where is it terminating? A is terminating to B. If you see, A is only having one terminal symbol B. Now check into the other production rules that how can you get B from this two production rules, how can you get B? You can get B if you replace this A with epsilon. Try to understand. You have, for this production rule, you have one terminal symbol B, that is A goes to B. After finding that, you will check that from this production rules, how can you get this B? So if you simply replace this capital A with epsilon, you can get the B. Similarly, for this production rule, do you have any terminal? No terminal, so do not consider this. Again, for the third production rule, what is the terminal? A, small a. How do you get small a from these two production rules? If you replace this capital A with epsilon, you will get the small a, which is the terminal symbol. So, since in all the cases I am replacing this capital A with epsilon, my final state is going to be capital A. Could I make myself clear? Why am I making A the final state?
Yes, ma'am.
Okay. So, if you want to check this for left linear grammar, please do it yourself. If you find any problem in understanding, you can ask me. I am not showing it here. So, that was all for today. I have more or less covered, tried to cover at least the miscellaneous portions of DFA and regular language. In the next week, one huge portion from this part is left, which is regular expression, which is another form of representing a regular language that I am going to start off with in the next class. Okay. So thank you so much. You can basically leave the meet and take your IMCRP tests. Thank you.